Right, let's start to graph our trig functions. So the first one we want to look at is the basic y equals sine x. So recall that this is our unit circle and we're looking at the value of sine. Let's start at 0. Okay, and what we're going to do at 0 is note that sine is the y value, sine is 0. So that's our first key point. Now let's go to pi on 2 and notice that the value at pi on 2 of sine has jumped up to 1. So there it is there. All right, over to here, and what we should find is that at 2 pi on 2 or pi, the value of sine has fallen back to 0. All right, and then over to 3 pi, we'll note that 3 pi on 2 will be -1. We're going to be down there. And finally, back to where we started. So to repeat the whole process, and it will be 2 pi will be back to 0. Okay. And so the way the trig function will work then is as I increase there, the increase in the y values will increase over this point here. So y values are going to creep up, max out at 1, come back down. Missed it. Back through there. Make sure your value goes through there, please. All right, when we list key sketch graphs, we list key features. So this maximum here is pi on 2, 1. This min here is going to be 3 pi on 2, -1. And our intercepts are when x is pi, y is 0. When x is 2 pi, y is 0. Now remember that this function will continue along there and continue along there. So we're going to put some arrows because it doesn't say over what domain. So the function that repeats itself regularly is called periodic, and the interval between the repetitions is called the period. Okay, the period of y equals sine x is 2 pi units. So it starts at 0 and will repeat itself every 2 pi or every time around the unit circle, because as the name suggests, going around in circles. Okay, going around in circles means we're doing exactly the same thing again, again, again. The distance between the mean position, so the mean line is this line across here, or the average value it's called of the function, is across there. And the distance between the mean position and the maximum position, so this position here and the maximum from there to there, is called the amplitude, and in this case the amplitude is 1. Now notice that the amplitude is always reported as a positive value. Okay, so it's always greater than 0. Okay, cosine works very similarly, but it's derived from, instead of getting y values, we get x values. So over here, we've got our starting point of cosine, and that's going to be at 1 because it's the x values that we're interested in. The cosine of 0 is 1. Now we go up to here, and what we note is the cosine falls down. So at pi on 2, the cosine is 0. Then we go over to here, the cosine is going to be -1. So at pi, it's going to be -1. And then over to 3 pi on 2, and over there, we're going back to 0. And at 2 pi, we're going back up to 1 again. All right, so let's draw this. All right, so make sure you do, like, these are turning points as well. So just note that it doesn't cut straight into that point. Many students will do it with a line going straight in, and that means that it sort of is a bit more V-like. So these are curves, okay? So they should ease into the turning points. All right, so this one here, the y-intercept is 0, 1, x-intercept pi on 2, 0. This one is pi, -1, that's the maximum. This one here is 3 pi on 2, 0, and that's also a stationary point, so we're going to say 2 pi, 1 is a stationary point. Chuck some arrows on your function there to indicate that that continues. The period of y equals cosine x is 2 pi. The amplitude is, well, the average value is along here. Okay, and the distance from the average value to the largest value is 1. All right, Now, here's an interesting question. What is the value of b in the following question? So we want the function sine x to equal cosine x. Okay. Now, how are we going to do this? Well, you'll note here that if I actually shift this function here over, what will happen is this value here, which would be pi on 2, will move to that spot. So what I'm going to say is sine x is equal to cosine of x take pi on 2, i.e. can you grab the cosine graph and shift it to the right pi on 2 units? Let's just see whether that works out. So I'm going to pull up GeoGebra here and show you how that looks. And this is an important thing to note. All right, so here is f of x equals sine x, and what I want to graph now is g of x equals cosine x. Now we can see there that that is the cosine graph, and what I want to do is shift it over. So I'm going to say take away pi on 2, and bang, the graphs line up perfectly with each other. So that's a handy way of noting that you can turn a sine graph into a cosine graph. You can also turn a cosine graph into a sine graph quite easily by some sort of translation. All right, so dilations. So we know from experience that dilations from the y-axis change the x values. So a dilation by a factor 2 from the y-axis will double all the x values, thus doubling the period. Okay, so if we do this, okay, dilated by a factor of 2 from the y-axis, many of you will be tempted to do this. All right, so double the x values. But recall that the answer is going to be y equals sine x on 2. Okay, so that is the transformation. Now, I'm going to do this via mapping just this once, just to show you how it works. So what we want to do is dilations from the y-axis change the x values, and we want to dilate it by a factor of 2. So I'm going to go 2x comma y. Remember, that's x dash and that's y dash. X dash equals 2x, x equals x dash on 2, and y equals y dash. All right, now what we're going to do is just do those substitutions into there. So x gets this. So our new function is y dash equals sine x dash on 2. So there you go, there's our dilation by a factor of 2 via mapping. Okay, so hopefully you can do that by recognition from here in, but we've just got to sort of know that there, when I see it, is not a dilation by a factor of half from y, it's in fact a dilation factor 2 from y. So what do you think a dilation by a factor of a half in the y-axis will do, or how will the function look? Well, I bet you the function looks like this, y equals sine 2x, okay? And what you do when you want to work out the period, recall, is you take the standard period of the sine function and you divide it by whatever this value here is, the coefficient of x, which in this case is 2, means the period is pi, okay? So what that means is it halves the period. The standard period is 2 pi, and what this 2 here does is it'll end up halving the period, or halving the time it takes to for the function to repeat itself. So here's the normal one going up to 2 pi. Here's the new one repeating itself at pi, where that is the function. Okay, so feel free to do the mapping for yourself on that part of the question there, but hopefully by recognition and from recalling from year 11 that you remember that. So the conclusion here is that dilations from the y-axis change the period. Okay, how often the function repeats itself. All right, dilations from the x-axis change the y values. So a dilation by a factor 2 from the x-axis will double all the y values. So the new function here is going to be y equals 2 cosine x. Again, what I'm going to do is map, 3, sorry, my bad. That should be a 3. So what I'm going to do is map this for once and once only. So dilations from the x-axis change the y values. So x stays the same, 3y, x dash, y dash. X dash equals x, y dash equals 3y, y equals y dash on 3. Right, let's sub in those definitions. So y gets y dash on 3 equals cosine of x dash equals, well, no, we can't say that. Y dash equals, I'm going to multiply both sides by 3, so 3 cosine x dash. So here's my image of the original function using the mapping, okay? But again, I hope you can do that by sight. What is the new function if y equals cosine x is dilated by a factor of a third? Well, again, you could use mapping, but hopefully you know that this is going to be the case. So dilations from the x-axes change the amplitude, okay? Okay, so this is just a bit of a summary of what we've just done. So given the cosine and sine function and a parameter at a and n, what we'll do is by varying these a and n values will affect the period, amplitude and range of the function. And varying this n value here will change the period by 2 pi over what we call the absolute value of n, okay? And the absolute value basically means we're just going to take the positive version of that number. So if n is negative, we'll just say it's positive. So for example, negative 15, if I absolute value that, the answer is just 15. And here's a summary of it down here. The amplitude is also the absolute value of A. So if A is negative 6, the amplitude is going to be 6. And then the range is going to be the negative of the amplitude followed by the positive of the amplitude, given that this graph has not gone either up or down. Okay, so let's do it for these two examples here. So we're going to state the amplitude, period, and range of them. So the A value in this case is negative a quarter. Therefore, we're going to say that the amp or the amplitude is a quarter. The range is going to be negative a quarter to a quarter. And our period is going to be 2 pi for the standard cosine function over the coefficient of the variable here, which is over 1/3, which is going to be 6 pi when you divide by that and multiply by the reciprocal. Okay, over here we've got an amp of 5. Our range is going to be -5 to 5. And our period for this one is going to be the standard period of the cosine function divided by the coefficient here, which is 4 pi equals a half. All right, so let's get a sketch graph going. All right, so this one here has an amp of 5, a period of 2 pi for the standard sine function over the coefficient of the variable, which is 3. Our scale is going to be 2 pi on 3 on 4, so we're going to split this into 4 parts, or we're going to divide the period by 4, so 2 pi on 3 divided by 4, which is going to be 2 pi on 12. And I'm going to leave that unsimplified to help us mark in these key points. So 2 pi on 12 is the same as pi on 6. So let's just have a look at our scale here, and what I'm going to try and do is just get one cycle of this going, and then use that one cycle to push through for as long as the domain's required. Okay, so what I'm going to do is write these numbers here as on 12s, okay, just to help me out. So this is going to be times 4 and times 4. This is 4 pi on 12. This is going to be 8 pi on 12. And of course, pi is going to be 12 pi on 12. All right, so now let's mark in our scale. So this is, we need to mark in 2 pi on 12, which is there, which is pi on 6. So what sine is going to do is going to start at 0, and sine, because I know the basic sine will go like that, it's going to go up first of all. So it's going to be 5 and pi on 6. All right. Then the next key point is going to happen at 4 pi on 12, which is there, or pi on 3. The next key point is going to happen at 6 pi on 12. Okay, so if this is 4 pi on 12 and this is 8 pi on 12, 6 pi on 12 must be in between. So 6 pi on 12 is pi on 2. So it's going to go up, down, and then it's going to be 5 and that point there. And it's going to come back up to 8 pi on 12 or for, what's that, 2 pi on 3, which is our period, which is definitely a good sign. Let's draw this one cycle of it. All right, so there's one cycle of it. And what we're after is to continue that for whatever reason. They want it continued from there to there. Okay, so they usually don't get you to do this many cycles of it, but they're allowed to, I suppose. Okay, so let's just mark in again our key points. There, 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 there. Yeah, this is a little tedious, I have to admit. Okay, let's continue it. Okay, and it's included, so I'm going to make sure that that's a clear filled in dot. That's also included. Okay, so it's going to go down to -5, up, +5. So all I'm doing is just completing the pattern here. Okay, there's no fancy maths going on. Okay, so getting a bit dodgy with the graph over here, but yeah, by and large, that's okay. All right, so now unfortunately what you need to do is label all the key features. So we got the origin there, that's pi on 6 comma, what's that, 5, and we've got to label the x-intercept, so pi on 3 comma 0. So I need you to do that for all the key points. I'm going to not do that here because again, we're just going to note that this is going to continue. You do need to label endpoints as well, which also happen to be x-intercepts. There are a key feature already, but that's something that you do need to do as well. Okay, so I'm going to back out there, and I'm going to either get you to note down that you have to label all key features, but this one's getting a little bit silly. Okay, so on to reflections. Okay, so the graph of y equals sine x is this. When it gets reflected in the x-axis, what we get is this graph here, okay, which when we reflect in the in the x-axis, remember we just drop a negative sign out the front there, okay? Now, when we reflect it in the y-axis, what we get is this graph here, which if I continued it on, it would be this graph here. Now, do you notice that that graph there, the blue one, is exactly the same as that one there? So actually, a reflection in the x-axis is exactly the same or yields exactly the same result as a reflection in the y-axis for sine. Okay, yields exactly the same result. And therefore, we're going to reveal this little thing here, that when you get y equals sine of negative x, you can actually grab that negative sign there and stick it out the front because it's exactly the same thing. Okay, this means exactly the same thing. And I think this move, I can't remember when it was, but a couple of years ago, this move was really required to further engage in a particular problem from exam 1, I think it was. Okay, so you do need to know that this is not a trick or anything like that. It's just that if you reflect in the y-axis, what you get is the same result as if you reflect the sine function in the x-axis. All right, so the graph of y equals sine x is actually what we call an odd function because it has rotational symmetry with respect to the origin. That is, if I pick up the original graph like that, using that as an anchor point, if I reflect at 90 and then 180, what I end up with is the exact same function. So y equals sine x is an odd function. Okay, what about cosine? Well, here's the standard cosine function. And if I reflect it in the x-axis, what I get is this, okay? And if I reflect it in the y-axis, what I get is exactly the same result, okay? So basically, there's no point reflecting cosine in the y-axis because it does nothing, And if it does nothing, what we should be able to conclude is that y equals cosine negative x is exactly the same as that. And again, that's what the notes tried to articulate there, is that reflecting in the y-axis does nothing, so therefore it returns you to exactly the same thing. So this is an even function, okay? So the function has no change if it's reflected in the y-axis. All right, so let's graph this one here between 0 and 2 pi. It's a little bit more of a reasonable domain. So our amp is 5, our period is 2 pi on 3. Okay, so we're dividing that by 3. And our scale is 2 pi on 12. It's actually virtually the same function. All right, now what we've got to know is what this negative sign will do to the sine function. So recall that what will happen is that's the standard sine function. This is the reflection in the y-axis. So when it's reflected in the y-axis, what I'm going to get is that, okay? Which if I continue it on, I'm just going to draw the continuation of that in a different color, is going to be that, which is exactly the same as a reflection in the x-axis. So I'm actually going to say g of theta is equal to negative 5 sine 3 theta. Okay, and I can conclude that for that reason that negative sign will go to there because it'll yield exactly the same result. Now, because it's there, it allows me to sketch this a lot easier. Okay, so here we go with the sketch. So we've got pi on 3, which is 4 pi on 12. Here's 2 pi on 12, or pi on 6. Here is 6 pi on 12, or pi on 2. This is 8 pi on 12. This is going to be 10 pi on 12. And this one here will be 12 pi on 12. All right, so let's pop in one cycle and then continue the pattern. So 0 is included and it's the sine function, so sine will start there. Now that sine function typically will go up and then come down, but this one here is negated, okay, because it's reflected in the x-axis or reflected in the y-axis, which is the same as a reflection in the x-axis. So what it's going to do is go down first of all. So it's going to hit that point, max out there, and then come back down to there. All right, let's draw this one cycle. Cool. All right, now that we've got that, we can just continue that pattern through to 2 pi. Again, it's probably a bit of overkill. Okay, VCAR examiners or even in a SAC, we probably wouldn't get you to do more than 1 or 2 cycles. It starts to get like, yeah, I get the point. So I probably should change this example for next year, but all right. So starting to get sloppy as I continue, but these first 2 cycles do look pretty good. All right, now again, you must label all key features, but I don't want to burn up a minute of viewing time on this video with me labeling the key features. So you go ahead and do that. Remember, endpoints must be labeled, maximums, minimums, and intercepts. Okay, all of those have got to be labeled. So you go ahead and do that. All right, so there's the exercise 6D. Okay, so get stuck into some graphing.